Hi students, today we'll discuss about the IR spectroscopy. You know, IR spectroscopy is included in the module 5 of chemistry syllabus, and chemistry is included in the first year BTech course. The code for the chemistry for odd semester is CH101 and for even semester CH201. Myself, Tanmoy Dotto, Assistant Professor, Department of Chemistry, JS College of Engineering, Kollani, welcome you in my class of IR spectroscopy. You know, your syllabus of IR spectroscopy is very brief. That means only the basic concept of IR spectroscopy is included. So according to the syllabus, first of all, we'll discuss about the very basic principle of the IR spectroscopy. So first of all, we'll discuss about the basic principle of the IR spectroscopy. Second, we'll discuss about there are different kinds of vibrational modes. Okay, so secondly, we'll discuss about the bond vibrations. Okay, different types of bond vibrations. Then we'll discuss about there are some conditions. Okay, what are the conditions of the molecules to be IR active? There are different conditions to be IR active. We'll discuss about that. What are the conditions for the molecules such that the molecules will be IR active? And the fourth, we'll discuss about the fingerprint region. What is the fingerprint region? And then we'll discuss about the application of the IR spectroscopy. Okay, so in the application part, and lastly we'll discuss about the application. So what I told you in the previous class also, that in the spectroscopy chapter, we'll discuss according to the application. That means what is the motto of the spectroscopy? There are different kinds of spectroscopies out there, like UV visible spectroscopy, like IR spectroscopy, like NMR spectroscopy, like mass spectroscopy. So different kinds of spectroscopy are available. So what is the motto of the spectroscopy, overall spectroscopy? The motto of the spectroscopy is the identification of the molecule or the unknown compound by different way. So there is a different angle of the characterization of the different spectroscopy. Okay, so in your syllabus, the very basic concept of UV, IR, and NMR, these are included in your syllabus. Okay, so here we'll discuss about the basic principle from the concept of the instrumental point of view. That means how we can determine the unknown compound or the unknown sample, or what is the basic principle behind the determination of the unknown compound. So that's why we'll discuss one by one things. So first of all, you have to know that what is the basic principle of the IR spectroscopy. So before going to the discussion about the basic principle, you have to know one fact, that you know that for any homoatomic molecule, if we take this is the compound A, this is the any compound A is connected with the B. Very basic things. Okay, so A is connected to the B, and they are connected with a single bond. So A and B, they are connected with a single bond. So if you think about that, or double bond, whatever, that means A and B are connected with a covalent bond. So if you think about that, A and B, they are two balls. Okay, this is one ball and B is the another ball, and they are connected with this. Okay, with the bond. Okay, so bond has a peculiar character like the spring. Okay, so if we think that the bond is like a spring, then we can draw the picture in this way. So these are the two compound, or here we consider the two balls, and they are connected with a spring, isn't it? Now when we think about the spring, then just think about that spring has a particular character like a vibration. That means if you think about the spring, then I think there is a peculiar character of the spring should come in your mind. this is called the vibration, isn't it? So spring means it will be vibrating, or it will vibrate. Now this structure, it looks like any kind of homoatomic molecules, like it may be H2. Okay. Now if we take any compound which are not homoatomic, they may be triatomic. Okay, there may be 3 atoms are attached. For example, the CO2. Then we can draw the structure like this. We can draw the structure like this. Okay. So now if we draw the structure in this way, it is the middle atom, it is the side atom, and it is the another side atom. And these 3 are connected with the 2 spring. Okay. This is for 1O, this is for the carbon, and this is for the another oxygen. Okay. So now what will be there? There will be some kinds of vibration. Okay. Now there, for homoatomic molecules, like the first case, there are only 2 types of vibration is possible. Okay. So either they will go to far away from each other, or they will come closer to each other. But here in the second case, there are different types of vibrations are possible. That means at this moment, this oxygen can go this side, and this oxygen can go this side. This is one direction. And again, these come to this direction, these come to this direction. In another way, they are also at a time, this oxygen come this side and this oxygen come this side, isn't it? So there are different way by which they can vibrate. So I will show you that what are the types of vibration possible for the carbon dioxide. Then I will tell you the basic principle of the IR spectroscopy. So now look this picture. Okay, so this is the picture of the carbon dioxide, and what there was that spring. There the spring is the double bond. Okay, so now if you see the first picture, look the first picture. In the first picture, there is the vibration, or there is the vibration of the 2 oxygen, but at a time 2 oxygen, their distance between the carbon, their distance increasing. For both the oxygen, in the same time, or after that the distance will be decreased. Okay, so at a time they going to far apart from each other, and they come close to each other. First case. And the third case, look there, when one carbon oxygen bond distance decreases, another carbon oxygen bond distance increases. Okay, so that means that these two types of vibrations are called here stretching vibration. Stretching means either bond distance will be increased or bond distance will be decreased, but there will not be any change in the bond angle. So first case stretching vibration, third case also stretching vibration, but the directions are different. In the first case, look, this is the symmetrical stretch. Why symmetrical stretch? Look, at a time they are going to same direction. That means they go outside at a time. After that moment, they are coming inside at a time. Both the oxygen, same phenomena for the first case. But for the third case, look there, when one oxygen come closer to the carbon, another oxygen go outward direction, isn't it? So at a time bond is stretched, and at a time one bond is stretched, another bond is compressed. Okay, so stretching and compressing occur parallelly. But in the first case, look there. There at a time both the bond are going to stretching or stretched or compressed at a time. So these two direction vibrations are called. First one is the symmetrical stretching. It is a symmetrical way, and the third one is called, it is the asymmetrical stretching. But middle one, look. Middle one, if you think about middle one, the middle one is the bending vibration. Why bending vibration? Because in the middle case, the bond distance are not changing. Both the bond distance remain same, but the bond angle, this is changing. Okay, so second case, these types of vibrations are called a bending vibration. So there are, in case of, if we consider the carbon dioxide, there are mainly two types of vibration mainly possible. One is the stretching vibration. Keep in mind, in case of stretching, their bond distance will be increased or bond distance will be decreased, but no change in the bond angle. But in case of bending vibration, their bond distance will not be changed, but bond angle will be changed. So this type of vibrations are responsible for absorption of the higher light. Why? I will show you. First of all, look this picture. Okay, so look this picture here. This is the range of the wavelength. That means in case of, if you compare the UV, IR, if you compare the NMR, etc., X-ray, then you can understand that these radiation differ from each other only from the wavelength or the energy. Or here, look here, it is the infrared or IR light which we are discussing today. That this IR light, or it is the wavelength range approximately 10 to the power minus 3 region. Okay, and UV, where is the UV? UV has the lower wavelength but higher energy. So what work will be done by the UV? So what work will be done by the UV that will not be done by the IR, because the energy which is coming from the UV radiation will not same with the energy which is coming from the IR radiation. So that's why in case of UV visible spectroscopy, UV was responsible for the electronic transition, but IR is responsible to change the vibrational level, bond vibrational level. That means if any compound is IR active, I will show you that how one compound to be IR active. So if any compound will be IR active, so the absorption of the light, the bond vibration level will be changed. Okay. So now what is the basic principle? The basic principle is that here, in case of infrared spectroscopy, that when energy in the form of IR is applied, and the applied IR frequency that equals to natural frequency of the vibration. That means if it match, okay, if the frequency which is coming from the IR light that match with the natural frequency of the vibration. Natural frequency means what I told you, that the bonds are vibrating. Okay, so if this vibrational frequency match with the incoming IR frequency, then what happens? The absorption of the IR takes place and the peak is observed. Absorption means same concept like UV visible spectroscopy. Okay, same concept like UV visible spectroscopy. What is the same concept? That if the IR light is absorbed, then after absorption of the light, that frequency or that range of the wavelength was missing. From the missing data, we can identify that where the light or where the radiation was absorbed by the sample. Isn't it? Okay. Now molecules are like the same things like UV also. Molecules are excited to the higher energy state from the ground state when they absorb the IR light. So basic principle is that when the bond vibration match with the energy which is coming from the as the IR light, then the vibrational range will be changed, and then we will get the vibrational spectra or the absorption of the vibrational light. Now come to the point, what is the condition of the molecule to be IR active? That means, is there any such kind of things that all the molecules will be IR active? Is it? No. All the molecules will not be IR active. So what is the condition of a molecule to be IR active? The condition of a molecule to be IR active, first one, either the molecule have permanent dipole moment. I think all of you know very well what is the dipole moment. Either the molecule has the permanent dipole moment, or the molecule or the dipole moment should be produced during the vibration, or the dipole moment it should be produced during the vibration. It should be produced during the vibration. Okay, so these two are mainly condition of a molecule to be IR active. Okay, so I will show you that how the vibration is changed or vibration is produced. Like if you think about the permanent dipole moment, then if you consider any of the homoatomic molecule, like if you think about the compound, of the like H2. So in case of H2, this is like, and both the atoms are same, both the atoms are H. So there is no question of the dipole moment. So dipole moment, how dipole moment is generated? Dipole moment is generated when there will be some difference of the electronegativity. There must be some difference of the electronegativity. If there is no difference of the electronegativity, there no dipole moment. So if it is the homoatomic or diatomic molecules, then there is that both the atoms are same, no question of the generation of the dipole moment. So any kind of diatomic molecules, okay, homodiatomic molecules, then it either it is H2, either N2, so they all are the IR inactive. Keep in mind, they all are the IR inactive. Okay, so why IR inactive? Because there is no permanent dipole moment or no question of the generation of the dipole moment during the vibration. Why? Because both the atoms are same, both the atoms are same electronegativity, so there is no question of changing the electronegativity. So that's why there we can't expect any kind of dipole moment during the vibration. So now another type of example. If you think about HCl, so HCl, obviously there is a change of the dipole moment, there is a difference of the electronegative. So if you think about the HCl, we can write down there is a delta negative and there is a delta positive, there is a permanent dipole moment. So if there is a permanent dipole moment, so obviously this type of compound will be IR active. That infrared radiation refers to broadly to the part of electromagnetic spectrum between visible and the microwave region. We already discussed about this fact, and here in the if you have to keep in mind that infrared spectrum we plot against the wave number in the x-axis, in the y-axis this will be the transmittance. Transmittance means what is the amount of light which is coming out from the sample. UV visible spectroscopy, there was the lambda versus, that means the wavelength versus absorbance, but here it is the transmittance versus the wave number. Keep in mind, okay? So that's why here wave number means it is a 4000 to 400 centimeter inverse. In this range actually IR spectroscopy work. When IR light is passed through a sample of an organic compound, some of the frequencies are transmitted through the sample without being absorbed. If we plot absorbed or transmittance, absorbance or transmittance, generally we plot transmittance against frequency, the result is an infrared spectrum. The infrared spectrum of a molecule is a result of transition between two different vibrational levels. Now come to the point that how infrared spectrum works actually. So infrared spectrum means if you think about that there are two vibrational range, okay, so this is the one vibrational range and this is the another vibrational range, suppose U1 and U2. So then if the energy from IR light is coming, then it will be the energy will be absorbed by the sample or the bond and it will move to the higher vibrational level. Just like the UV visible spectroscopy, the electrons absorb the energy and it jump to the higher energy level. Here the same case, here it is the vibration, okay, but if the energy is coming, its vibration will be increased and it goes to the higher energy stage. That is the same case, okay, like the electrons, okay, here bonds are vibrating. If the same energy or same the frequency available from the outside, the bond vibration will be increased and it goes to the higher energy level. So in this way, the absorption of the energy occur, or the absorption of the radiation occur, and which energy is not absorbed by the sample, okay, or which energy or which radiation or which range of the wavelength is not absorbed by the sample, that energy or that radiation coming out from the sample without any problem, without any interference. So that coming which energy is coming out from the sample, this is called actually transmittance or transmitted light. So if we plot that the transmittance versus your wave number, then we'll get this type of curve. Okay, so here it is the negative curve actually, because the peak denote the negative peak, this type of negative peaks, this denote their transmittance is very lower. Transmittance is very lower means absorbance is higher. That means this peak indicates that actually here absorbance occur. Okay, in this region actually absorbance occur. This peak indicates that. Okay, so from this negative peak, that means transmittance versus your new bar or the wave number, we can understand, okay, where maximum absorbance occur. Now look how or what is the application site of the IR spectroscopy. That there are some groups, okay, there are some groups for which we know that what will be its absorption value or the wave number value. So if you think about the alcohol, ether, carboxylic acid, then look here, there is a particular value of 1300 to 1000 centimeter inverse. So for any unknown compound or unknown sample, you don't know what groups are present in this unknown compound. If you get any peak in this region, then you have to understand, or you have to think that, okay, my sample contain maybe there's some alcohol or ether groups. In the same way, if aldehyde, ketone or ester present, then there may be a peak in the range between 1750 to 1680 centimeter inverse in this region. If there any kind of chance of the amide, then you will get a peak in between 1680 to 1630. If there is any amine or amides, then you will get the peak 3500 to 3100. So in the same way, it is just an example. There is a long list of the or chart available for the individual groups, or the range of the peaks available for the groups. Okay, so if you get any kind of peak in this region, then you have to understand that in your unknown sample or in this unknown sample, there is a chance of this type of groups may be present. Clear? Okay, so this is the application site, or what I told you, that the beauty of the spectroscopy is that the spectroscopy is used for the identification of the unknown sample. Actually, in this way, we understand that which groups may be present here. Now come to the another topic. This is called the fingerprint region. What is the fingerprint region? Fingerprint region means there is a region of the your IR spectroscopy in the range of the 1430 to 910 centimeter inverse. Keep in mind. So this range is called actually fingerprint region. Why? Because this range contains many absorption bands caused by bending vibration, and also the absorption bands caused by several stretching vibration. That means in this region, okay, if you look the graph, okay, in this region, actually this is the fingerprint region. This region is called the fingerprint region. Okay, so in this region, for the maximum compounds, there are so many small peaks. We can expect the small peaks actually, and peaks are overlapping with each other. Okay, if there is a very small peaks or overlapping peaks are available, then what is the expectation? The instrument is also unable to give the each and every individual peak. There is a chance of the overlapping a broad peak, and this looks like a finger of the human being. Like, you know, if you think about the fingerprint of the human being, then you can understand that there are a fixed or a particular type of the fingerprint you can expect from a particular human being. Okay, so like this fingerprint region is also like this. Okay, this is the identification part of the compound of a compound. Okay, this is the fixed for each and every compound. So that's why this region is called actually fingerprint region. This is very important question. You have to keep in mind that what is the fingerprint region. Now come to the part of the application of the IR spectroscopy. What is the application of the IR spectroscopy? So in IR spectroscopy, first of all, IR spectroscopy is very much able to determine the various types of the unknown groups. Okay, what I told you, that either your sample contain the carbonyl group, or your sample contain the alcohol group, or your sample contain the ether group, or like this. Okay, so this type of unknown groups, we can get the information from the peak of the IR spectroscopy. From the peak of the graph of the IR spectroscopy, we can understand, we can predict what types of groups may be present in the unknown sample. First. Second, determination of the purity of the sample. That means IR spectroscopy, although if you know the graph of the IR spectrum of the unknown sample, then in the if you check the sample, that if there is any extra peak corresponding to the peak of the pure sample, then there is a probability of there any impurity sample present in the compound. That's why we are getting the peak for the contaminated sample, peak for the sample which is present in the or mixed with the pure sample. So in this way, we can identify by checking the graph or standard graph of the sample, we can identify the purity of the sample. Study of chemical reaction, same case like with the UV visual spectroscopy, we can understand also that that how the chemical reaction is proceed. Like if there is any reaction, there some bonds are breaking and some bonds are formed. Okay, for example. Okay, so if you take the sample mixture, sample from the reactant and the product side, then you can from the how the graph is changed with from time to time by checking the graph or the peak value, then you can understand that okay, that the product is formed gradually and the reactant is gradually converted to the product. By this way, you can understand that what will be the chemical you can study the chemical reaction also. The third case, that is very important, you can understand that either in your sample there is any kind of water sample present or not. In your sample, either there is any kind of water sample present or not, you can also understand from the IR study or IR spectroscopy. Okay, so because if your sample contain the H2O molecules, if there is any H2O molecules, then you will get a peak for the H2O molecules, isn't it? That means with your pure sample, sometimes it is not possible to identify either any H2O or water present or not. And sometimes the reaction condition that should be very dry, that if there is any moisture present in your sample, there may be some kinds of problem in the reaction. So if to check for these things, we have to take the IR spectrum. If your IR spectrum graph there is any peak present for the H2O, that indicate that your sample is not 100% dry. So this is very much important for the reaction also. So these all are the applications of the IR spectroscopy. So then what you have to actually study or what you have to understand properly, first of all, you have to understand the range of the IR spectroscopy. Okay, so IR spectroscopy actually what spectroscopy is included in your syllabus, UV, IR and NMR. The energy, if you compare the energy of the IR is the middle in between the UV and NMR. Okay, and basic principle, IR spectroscopy mainly it is utilized by the molecules to change its vibrational level. Okay, that means what energy is coming from the IR level, that this energy is utilized by the vibration to change the vibrational level of the molecules. Now the next question arises that all the molecules will not be IR active, like homodiatomic molecules will not be IR active. To be IR active, the molecules should have the permanent dipole moment, or the dipole moment should be changed during the vibration. So for this case, we can take that HCl, this will be the IR active molecules. On the other hand, carbon dioxide also IR active molecules. There are two things from the different point of view. HCl, it has the permanent dipole moment. Carbon dioxide, it don't have the permanent dipole moment, but the dipole moment will be produced during the vibration. That's why it is also IR active. Third condition or third things which you have to keep in mind, that there are some groups which have the particular wave number value or the IR absorption value that is fixed or standard chart available. So if your unknown sample gives such kind of peaks, then you have to understand, okay, your sample contain this kind of groups. And then fingerprint region, this is also constant for a particular compound, like the finger of the human being, it looks like. Okay, so by this fingerprint region in between 1430 to 910 centimeter inverse, we can understand, okay, this is the in this region what is the peak we will obtain. This region is called actually fingerprint region. And finally the application, this is very, very important, what you have to do. So that's all for today's class. Okay, so you have to read all the things properly. Okay, and thanks to all of you for attending my class. Meet with you in the next class with a different topic. Goodbye.